Hello, in this lecture 9 we'll continue with our discussion on entropy method, and we'll present the two main tools used in entropy method, namely that of tensorization and Log-Sobolev inequalities. Just to refresh your memory, recall that entropy method builds on so-called Herbst's argument, and we presented what Herbst's argument is last time, but this time I'll quickly review it so that we can refresh your memory. So consider a random variable x. I'll present a slightly different form than what we saw last time, and this form is slightly more abstract, but I think you can digest this generalization. So we have a random variable x defined on a probability space. So recall what all do you need to define a probability space? The input set omega, this is the universe, and then the sigma algebra sigma, and this probability measure p. Okay, this is what a probability space is. This is a set of events, this is the universe, and this is the probability measure. So consider a random variable defined on this, and define a new measure q. Instead of p, we define a new probability measure q, which is absolutely continuous with respect to p, and is given by, so it has a density with respect to p, given by a density with respect to p. We can just define a density with respect to p is given by e to the power x by expected value under p of e to the power x. Okay, so this is just a definition. Then we showed this very nice formula for divergence between q and p. Last time we were writing this whole thing in a slightly different way. We were using the measure q we were looking at was e to the power t times f of x. Okay, but it's exactly equivalent. Okay, so the formula that we have is dq by dp. The divergence between q and p. Yeah, let me put a t here. This divergence is equal to this divergence by t square is equal to the derivative of the log moment generating function at t divided by t. Okay. So this is some function, its derivative is dq, the divergence between qt and p. Okay. This is this formula which we can treat as, which leads to Herbst's argument. Okay, so how do we use this formula? Well, it gives us a nice formula for log moment generating function. It gives us px lambda is equal to lambda times integral 0 to lambda d qt p by t square dt. Okay. This is the alternative form. So if you want to derive an upper bound for the log moment generating function, then it suffices to derive an upper bound for this. So that's what Herbst's argument is. So Herbst's argument says that if d qt p by t square is less than equal to say v by 2 for all t greater than 0, then then the log moment generating function is less than equal to lambda square, because you integrate v by 2, so that's lambda square v by 2 for all lambda greater than 0. Okay. All right. So this is Herbst's argument. So we just have to derive a bound for this particular divergence, and that will give us a bound for log moment generating function. And that's what we want to do now. Note that So our interest, we are interested in product measures, in product E, okay, which we associate with different coordinates of our random variable. So px1, px1 times px2 pxn. So this is our n-dimensional product measure, and x we will replace with our function f of x1 to x. Note that so that the sample space omega is this product set here. Okay, so omega is x1 cross. That's where we are interested in. And for this thing, we have to derive a bound on dqt by dqt on p, and it will turn out that uh, the first thing we will do is we will show that although we want to derive a bound for n-dimensional case, it suffices to derive a bound for one-dimensional case, and that's what is called the tensorization part. Okay. So this general recipe, general entropy method recipe, as we saw last time, has two parts. So first step has two steps. First step is tensorization. Suffices to establish a bound for one dimension, okay, n equal to 1. And the second step is some inequality, a basic inequality, which is for one dimension. Typically these are called log. Typically we use what are called Log-Sobolev inequalities. It's not a single inequality, it's sort of a family of inequalities, and we will not even go into the origin of this name for now. Later in the course I'll return to these inequalities, and then perhaps I'll have a more elaborate discussion on this. Okay, but for now you can just imagine this is some elementary inequality for n equal to 1. Okay, once we have these two things, then combined with Herbst's argument, we get give concentration bound with Herbst's argument. When you combine them with Herbst's argument. Okay, that's the general plan here. So let me show you both these steps now. What do we do in the tensorization step? How do we tensorize? We want to bound this quantity. What we will show is that it suffices to bound some similar one-dimensional quantities. Okay, that's the tensorization step, and then we'll show Log-Sobolev inequalities. That's the plan. Okay, so let me start with this. Was all review. Let me start with the first part. Tensorization of divergence. This Kullback-Leibler divergence. So before I do this, let me review some simple properties of this Kullback-Leibler divergence. So recall that dQp is defined as expected value of, if Q has density with respect to P, this density is noted by dQ by dP, then it's defined as dQ by dP log dQ by dP, density with respect to P this. Otherwise it is, let's say, infinite. That's how this guy is defined. In particular, for discrete distributions Q and P on the same set X, so discrete set X, dq P is equal to summation over X. Note that when P is the bigger measure here, whenever I'm not writing an expectation here, it is clear that the expectation is with respect to P. So since you take expectation with respect to P, it is the same as taking expectation of this guy with respect to Q. It's the same thing because that's how this expectation is defined. These are some small gymnastics. So once you get comfortable with this idea of densities with respect to another distribution, redound-Nicodim derivative, these are called redound-Nicodim derivatives, then you can do these manipulations. Okay. Yeah, so that's the whole idea of density. When you want to compute expectation with respect to Q, you can actually compute expectation with respect to P, but multiply it with the density. So that's why these two things are exactly the same. Okay. All right. So for the discrete case, we can write this as summation over X, Qx, taking expectation with respect to Q of the log likelihood ratio of this density. That's Qx by Px. And this is only true when Q is absolutely continuous with respect to P, which in discrete case happens if the support of Q, the set of point where Q is non-zero, is contained in the support of P. And it's infinite otherwise. Okay, so this is what Kullback-Leibler divergence is. We saw this last time. And this comes up in our in Herb's argument. Alright, so now I'll quickly review two very basic properties of this guy. So first property is that it is non-negative. How do we show that? So we'll use Jensen's inequality for this. For discrete case, you can perhaps show it easily. Actually, it can always be shown easily. So dqp, the general definition is expected value with respect to P of expected value with respect to P of dq by dp log dq by dp. So if we think of this guy as a random variable, this guy is a random variable x. Let's just call it x, just defining it as x. So this guy is expected value over P of x log x. Okay. And so which is the same as expected value, just dropping this P part here, of f of x, where f of t is defined as t log t. So what do we know about this function t log t? So at this function t log t, how does it look? So as t goes to infinity, this goes to infinity, and as t goes to 0, what happens to this function? So in the limit as t goes to 0, this function also goes to 0. Okay. So this function f prime t is, it looks like, what is f prime t here? f prime t is 1 plus log t, f prime t is 1 by t, and which is greater than equal to 0 for t greater than equal to 0. Implies ft is convex, right? And therefore the average, so it's convex. Maybe we can just try to plot it. It's convex, and it is negative for t between 0 and 1, and then it is and at t equal to 1 it is 0 and 0 here, and then it goes up all the way to infinity. So it's something like this. Okay, note that it has only one point where the derivative is 0, so that also comes out here, and yeah, that's what this function looks like. Therefore, since this is a convex function, so the value at its average at average is less than average of values. So this implies by Jensen's inequality, expected value of fx exceeds, so this is what our dqp was, expected value of x, this exceeds f of expected value of x. So what is this f of expected value of x for Rx? Our choice of x is f of expected value under p of dq by dp. Okay. I'm deliberately writing it in this language of Radon Nikodym derivative so that you become comfortable with this. So now note that the way this density is defined, if you want to take expected value of a function with respect to q, okay, you can do that, and you can switch to the expectation with respect to p by multiplying it dq by dp. Right? So these two are equal. So this is equal to this. And this is 1, so this guy is just 1. So that's just equal to f of 1. If you want to understand this proof further, you try to rewrite it for the discrete case. You will understand each of these steps better. Okay, I think that's a very important exercise you should do. Alright, so now what is f of 1? So this is 1 log 1, which is 0. Alright, so we got our bound. So this is just by Jensen's inequality. dqp is non-negative. That's the first property you want to cover, that dqp is non-negative. So first property, dqp is non-negative. Second property that we have is about is what is called chain rule sometimes. So suppose you have p and q probability distributions on, say, x cross y. Okay, so we will use the notation pxy and qxy, okay, for the joint distribution. So we will imagine this random variable x and y, and p and q are distributions for this x and y. Then we can relate this. Let's just. So then we can relate this qxy to pxy. This is equal to summation. Actually, so the divergence of the first coordinate. This is called the chain rule for divergence. So divergence of the first coordinate is qxpx plus d of qy given x, py given x. Note that these guys are both random variables because these are conditional distributions. Okay, so first chi and then the conditional distribution of next two conditional distributions, and you have to average this chi because these are conditional distributions. So this becomes a random variable. So you average it over some distribution of x, and that distribution is the first one here. So qx. Okay, so this is the formula. Uh, yes, this is called chain rule for divergence, and this will be very useful for establishing the tensorialization property we are looking for. So if you have divergence between qxy and pxy, it can be decomposed into divergence between the first part and the conditional divergence. This second quantity here, uh, you can verify that this is by just the form for discrete case. You can easily verify this is also equal to divergence between um, qxy and qx py given x. That's the distribution between x and y when x is distributed with x and y is distributed as py given x. So this guy here is qx py given x of x comma y. The joint, let's say PMF, is qxx py given x y given x. Okay. All right. Okay, so this is equal to this, and it has other. This is another notation. It is denoted by conditional divergence. dy given x, p given x. Condition on this averaging measure qx. These are all the same things. This guy, this is equal, and this notation denotes these guys. That's what we will show. And an important consequence, in particular, if qxy equals to qxqy, so it's a product measure, they're independent under q, and pxy equals to pxpy, then divergence is just additive. D qxy pxy is equal to d qx px plus d qy py. Okay, so that's the claim. So how do we show this? Proof is simple. You can just expand things. I'll give an informal proof. First, you notice that we can assume that qxy is absolutely continuous with respect to pxy. Okay, this is just some. Maybe I should not prove this for the general case. It will look very technical. I'll give the proof for discrete case. For discrete distributions. So discrete distribution, the proof is very simple. This divergence here, qxy pxy, is equal to expected value with respect to qxy when the support is contained. Otherwise, they're both infinite. So I can assume, without loss of generality, assume support of qxy is contained in the support of pxy. Because if this is not true, then both sides here will become infinity. You can check that. So then you have qxy of x comma y. So this expectation is for this x comma y by pxy of x comma y. Okay, so these are the random variables, and the expectation is with respect to these random variables. So this is equal to expected value with respect to qxy of log of qx by px plus log of qy given x by py given x. Okay, and this guy here is exactly equal to, so what is the expectation of, this is a function only of x, so this part of y over y disappears, so what you get is just this guy here plus now expected value over qx and expected value over q of y given x, because that's how expectation works. This is the conditional expectation given x under q of log of q of y given x, y given x, p of y given x, y given x. Yeah, so this notation is a bit ugly, but what I'm saying is the expectation of this guy can be written as expected value of the conditional expectation, and the conditional expectation will happen to be with respect to q of y given x, and the outer expectation is qx. So when you do this, what you get here is, this is just, the first term is just dq2, and second term is expected value over qx of, what you see inside is d qy given x, py given x. More or less elementary proof. Okay, it's by definition. Okay, so that's what we get. So this was the second property that we wanted to cover, that this chain rule here. Okay, so note that we did it for two random variables, but you can do it for multiple random variables. So if you have xn and pxn, that is equal to summation t equal to 1 to n, or maybe rather I equal to 1 to n, divergence between q of xi given the past under q, p of xi given the past under p, and now this is a random variable depending on x minus x, the past, and so you take expectation with respect to the past but under the measure q. Okay, so more succinctly, this is represented as conditional divergence. Somehow this conditional divergence notation is very handy, but it's not so popular outside the information theory literature. Okay, so that's what this divergence is. Alright, so we have these two properties, chain rule and the non-negativity of divergence. Now using these two properties, we'll establish our main result. So some notation. Recall that we had this this measure we were showing, pi, and pi was a measure when you, pi was basically a conditional distribution given everything but the ith guy. So given xi minus 1 and xi plus 1 to n. Okay, so we'll introduce a notation for this guy. Let xi be defined as everything but the ith guy. This is a random variable which appears in which appeared in afferent sign inequality. Okay, so this is the notation. X superscript I, superscript because this is a vector and it's everything but the ith guy. Just like these notations, this I minus 1 was everything up to I minus 1. This one is everything starting from I minus 1 plus 1 to n. And this is everything but the ith. So with this notation, here is a lemma. And I'll call this the entropy tensorization lemma. So consider independent random variables x1 to xn under P. Let q x1 to xn be any other distribution. Then divergence between q is the overall thing, and p, this is basically divergence between q x1 to xn and p x1 to xn. This divergence is less than or equal to summation I equal to 1 to n expected value with respect to this q of x, everything but the ith guy. Okay, divergence between q x of the ith guy given everything, p the ith guy given everything. That's the claim. Sort of a very interesting claim. Looks something like chain rule, but we are not conditioning on the past. We are conditioning on everything but the ith entity. So all these divergences are just changing one part of the function, okay, of the measure. So it fixes everything but just changes one part. Okay. And I'm calling it entropy tensorization lemma, but we don't see entropy anywhere. We'll see entropy later. By the way, I never reviewed in this class what entropy is. Recall that in the last class we introduced this entropy of F, and we showed that this entropy of F is exactly equal to we defined it as this is some side note, it's a little bit of a digression. So entropy of any function we had defined as expected value of fx log fx minus expected value fx log of expected value fx. That's what we define entropy to be. And divergence between this q of f, so q of f we had defined as a tilting with respect to f. So this was e to the power fx, that's a tilting. From this p is exactly equal to entropy of f by expected value of this divergence is exactly equal to entropy of e to the power f by expected value of e to the power f. Okay, so this formula from last time, this divergence can also be related to this ratio. This is just by definition. Okay, so since we are establishing some tensorization property for this divergence, that will tantamount to tensorization property for entropy. Okay. Of course, we are assuming here this expected value of e to the power f is 1. That's why divergence looks like entropy. Uh, and that we can do for most of our proofs. Yeah, so we're just calling it tensorization of entropy, but actually we're showing some tensorization for divergence. Okay. All right. Okay, so now we have this claim. How do we show this? So proof just by chain rule for divergence, by chain rule for Kullback-Leibler divergence, dqp dqp is equal to summation I equal to 1 to n d of q expected value over the past, divergence of q xi given the past from p xi given the past. Okay, that's equal. So, and we want to show this less than this. So we can just take the difference of these guys and show that the difference is non-negative. So consider summation I equal to 1 to n expected value over q of x I of divergence between q xi given xi. Okay, so right. So this claim, the most important thing in this claim is that these guys are independent under P, and so under P there is no past. Okay, it's just Pxi. That is the most. Otherwise, actually, this bound doesn't hold. You can find a counter example. So this is only for independent case. So yeah, so this is Pxi, and similarly this guy, because they're independent, this is only Pxi. Doesn't depend on what the past is. Right. So the difference of these two terms would be this from Pxi minus the expected value under Q of the past of divergence between Q xi given xi minus 1 from Pxi. Okay. And so let's now look at each term here. So we just consider this guy here. So this guy is it can be written as expected value of this, and let's just look at a discrete case. So there will be expectation with respect to this conditional distribution of log of probability here and probability here. It can all compactly be written as the first term, expected value over q, the entire q of xn, of log of q of xi given the past by p of xi. Okay, this is what the first term will turn out to be. So there are two steps here. I had an expectation of a q xi outside, and then there's an expected value which comes in the definition of divergence. I could have done this here also. Maybe it's something good to put it down. I have to put down here. Yeah, so I had all these guys here, right? So one more way to define conditional divergence is you can take expected value with respect to qxy of log of qy given x by py given x. I should put some derivative, but let's just look at a discrete case. So that's just y of. So this y and x are generated from q. That's what this divergence is. It's equivalent. So you will have this conditional expectation inside that makes the conditional divergence, and then the outside expectation, which you can combine to get the overall expectation. Okay, so this is first term, and the second term again is expected value with respect to q of xn log of q of xi given xi minus 1, xi given xi minus 1 by p of xi. So this sort of harmless trick of writing both in terms of common distribution is something which will come up again and again in this course, and this is sometimes called coupling. In principle, these two quantities didn't require a common joint distribution. They were two different quantities related to two different distributions, but we realized that they can both be expressed as coming out from the same joint distribution qxn, and the advantage of doing that is that I can take this expectation, the common expectation, outside and take both these quantities inside. So you have log of this minus log of this. This pxi part cancels. And this is where we have used independence, because otherwise you would have conditioning on xi here and x past x minus I here and x past here. So now you just have this one. So now what is this guy? Xi given x minus 1. This again can be written in terms of, this is your P, this is your Q, and you're looking at this conditional divergence. So this is conditional divergence. Maybe, I don't know, maybe a better notation is that of conditional divergence. This is the conditional divergence between xi given x past from another measure where we just take the marginal given only the first I minus 1, not minus I part, and averaged over x of I. Okay, and this guy must be non-negative. So this guy is non-negative. Alright, so this difference, each term in this difference is non-negative. Therefore, the overall difference is non-negative, and therefore this guy exceeds this guy. That's the proof. Nothing very difficult. Actually, it looks all very simple because that's how profound this method is. So now what we do is we apply this sort of tensorization property of divergence to get a tensorization property of entropy, because we have called this entropy tensorization lemma. Let's see how we get tensorization of entropy from this. And recall that the definition of entropy for us was expected value of f log f, okay, minus expected. This is the definition of entropy that we have. And for the particular case where so the entropy of f by expected value of f, can be a better way to say is, if expected value of f equals to 1, which is something we'll assume for now. By the way, this entropy is defined only for non-negative functions f. Okay, otherwise they are log of a negative function, which doesn't make sense. So this is the definition. For now, let's assume just this part, that expected value of f is 1, and we'll see that this can be removed later. So under this assumption, consider a q which is defined by dq by dp equals to f. Just like we had seen earlier that we had e to the power lambda f, now we are defining dq by dp equals to f. For this q, we saw that the divergence between q and p, which could be bounded above using that tensorization property, but this divergence is exactly equals to expected value of dq by dp log dq by dp, and this is exactly equal to entropy of f. Okay, so for this q, this divergence is exactly the entropy of f. Okay, and we saw that this entropy of this divergence is less than equal to summation I equal to 1 to n expected divergence, expectation over expected value over this qxi. So q of all but the ith guys of divergence between qxi given all but the ith guy and pxi. Now if you look at this guy, this can be expressed as summation I equal to 1 to n expected value over q, the whole q now, xn, of log of qxi given xi by pxi. D of this. So now we need to convince ourselves that in fact this measure is absolutely continuous with respect to pxi, and their log likelihood ratio can be expressed in some nice form. So let's look at that. So d of qxi given xi by dpxi, and this random variable, we will look at it as a function of xi, but of course we have conditioned it on all the paths, so I'll use this notation of conditioning here. Okay, this guy here is equal to, okay, you can verify this part maybe by using a discrete case. This is equal to the f of xi given xi. Okay. F of xi given xi divided by the conditional expectation under P of f of xi given xi. Okay. So this is P, conditional expectation over P of xi. This is the random variable given the past. But P, this doesn't matter because P for independent measure, this is just leverage only over xi. So this is something you can verify. You can verify it for a discrete case because the product form of P, you can show that this one also has this form. And therefore, by observing this guy here, if you continue from this point, this expression here is exactly equal to summation I equal to 1 to n expected value over q log of I didn't define this notation. This is just my notation for x I minus 1 xi xi plus 1 to n. Right? So you have all the remaining arguments and the ith argument. It's just for convenience. So this becomes log of f of x, so then the q by f of x divided by expected value, the p, it's better to write it as f of xi given xi, and under p f of xi given xi. So if you look at this quantity here, this would look like summation I equal to 1 to n expected value under P of fx, and we have assumed that expected value of x is 1, so there is no division required, log, and this fx we can write it as f of xi given xi log f of xi given xi. This is just f of x written differently for a specific reason, minus expected value over P of f of xi given xi log of expected value over P of xi given xi. So essentially what this thing we have written here is I equal to 1 to n expected value of entropy, but given all but the ith coordinate of it. Okay, this is similar to the Afrenstein form that we saw earlier. Okay, so we have the Afrenstein for entropy. We show that entropy of we have shown that entropy of F is less than equal to summation I equal to 1 to n. Sorry, n expected value entropy given everything but the ith coordinate of F. Okay. And we have shown it only for the case when expected value of F is 1. But now you note that if you divide both these sides with a constant, okay, this is true for expected value of F. This is if expected value of F equal to 1. But if this inequality holds and then you divide both these sides with a constant, then still the inequality holds. And therefore, this can be removed. So this condition can be removed by dividing both sides with expected value of it. It's a non-negative function, so we can do that. Okay, so this is something that we will retain from this lecture. This is the Afrenstein counterpart of entropy, and we'll call this a tensorization property of entropy. And it just follows from the tensorization property of this divergence. Okay, that's something we'll retain from this lecture. Okay, so I think this is becoming a long lecture already, so we'll stop here. And in the next class, I'll show the binary Log-Sobolev inequality.